In this video, I want to go over section 4.3. Hopefully you've already looked through this on your own, tried to make some sense of it, so I want to highlight the main points, and then afterwards, probably in a separate video, I'll do an example. Okay, so section 4.3, page 278, is on derivatives and the shapes of curves. And first they talk about this mean value theorem, which I've never found terribly useful. It's just kind of the thing that says if you have an interval, somewhere in between there's got to be a maximum and a minimum in that interval, which, okay, it kind of has to be, right? If you have from here to here and you connect it, there's got to be a place where it's the biggest and a place where it's the smallest. So I don't know. Yeah, it's kind of obvious. So you can skip through that pretty quickly. The main ideas that you really need to get are what's inside these red boxes. This is what you got to keep referring to because it gets confusing sometimes, and you go back to what's inside these red boxes, maybe copy those down on a piece of paper somewhere. But let's just go through those then to focus on that. So this first red box is an increasing decreasing test. If the derivative is greater than 0, that means it's increasing. Okay, this is all, again, most of the stuff makes sense. That's the nice thing about this. If the derivative is greater than 0, that means the slope is greater than 0, which means it's a positive slope, right? If f prime of x is greater than 0, that means the slope is positive. That means it's going uphill, so it's increasing. Again, okay, maybe it sounds confusing, but it's kind of obvious. If the slope is less than 0, if the derivative is less than 0, that means the slope is negative, so it's decreasing there. It can be changing, but it's still decreasing, right? So this is all decreasing. So all you're looking at is it going uphill or downhill. Okay, so that's all that one is. So that kind of makes sense, just where the derivative is positive or it's negative. Okay, then they do some examples which you should look at. Okay, now, other stuff with the first derivative. Okay, suppose that c is a critical number of a continuous function f. Okay, so there's no jumps in it. It's continuous. And remember, a critical number is where either the derivative is 0, so it's like a max or min or something, or where the derivative is infinite, where it doesn't exist, where the slope gets infinite. It's continuous, so we don't have any jumps, but still we could have an infinite slope, perhaps. So actually, is that possible? If it's continuous to have an infinite slope in there. Yeah, I guess if you go to infinity, but probably that's not a major concern if it's continuous. Okay, so no, actually, sorry, it could be if we have like a sharp point, let me think, a sharp point like this or something where it goes down and then comes back up. That's continuous, but it has an infinite slope. Like the edge of a circle. Like right there, it's an infinite slope. I don't know. Anyway, that's a minor point. Okay, so we have a critical number. Slope is 0 usually. So if f prime changes from positive to negative, then it's a local maximum there. So if the slope changes from positive to negative, and the slope is 0 at c at a point, it's a local maximum, which of course makes sense. Like right there, slope is 0. Okay. The slope goes from positive to negative, so obviously it's a maximum. Okay, and then if it goes from negative to positive, it's a minimum, which again, this stuff makes sense. So here's a minimum. Slope goes from negative or decreasing to positive, and so it's a minimum there. Okay, that makes sense. And then if it does not change sign, then it's not a minimum or maximum, and that's again one of these things here where the slope is negative and it's still negative, and right there the slope is 0, right? F prime is 0, but it's not a minimum or maximum. So one of those points, it goes negative, negative, or it could go positive to positive if I drew it like, yeah, I always have a hard time drawing these. Positive, positive, I go like this, so right there. So there it's 0, positive, still positive. Then again, we can't say it's not a minimum or maximum. And they draw some pictures of those here. They do a better job than me. See, the slope is 0, but it's not a minimum or maximum. Okay, that's all makes sense. The stuff does all make sense, which is good, but the definitions are tricky. Okay, now here's another thing, concavity. Concave upwards is an interval where the graph, the derivative is always increasing. Then it's concave up, concave down is when it's decreasing. So here, this curve would be concave up because the derivative is always increasing. In other words, it starts off negative and is always getting more positive, right? Getting less negative. Here it's getting less negative to 0 and getting more and more positive. So the derivative is always increasing. F prime is always increasing here. And so they call that concave up. This one, the derivative is always decreasing. Starts off positive, or we're taking away from the positive number. It's getting less positive to 0 to more negative. So the derivative is always decreasing, getting more and more negative. Even though it's positive, it's getting less positive. So that would be concave down. And again, you just kind of like holds water pointing up here. Concave up, concave down. The water falls down, falls out of the bowl. I don't know. Okay, but so that's another big definition. And again, it's pretty obvious. It's when the derivative is increasing, when the derivative is decreasing. So that's the concave up and concave down. Now, here's a tricky place. One of these guys, at this point, here the derivative is increasing, getting less negative. So this is concave up. And on this side, it's decreasing. So on this side is concave down. So if you have one of these types of points, and by the way, this is called an inflection point. An inflection point is when it switches over from concave up to concave down. So one of these points is it's called inflection point. That's where it switches over. So you got to be careful of those points there. Okay, so that's the concave up, concave down stuff. And then they give some examples and everything. Now, how do you tell? So here they have this next red box is a concavity test. If the second derivative, okay, so now we're going to take the derivative twice. If the second derivative is greater than 0 at a point, then it's concave up. Okay, and why does that make sense? Well, let's look at their graph right here, right? So let's think about what the second derivative tells you. The second derivative tells you how the slope is changing, right? The first derivative is the slope, and the second derivative tells you how fast the slope is changing. If the second derivative is greater, that means that the slope is getting more positive. Okay, so like right here, the slope is getting more positive, right? It's getting less negative. So the slope is changing in a positive way, which means the second derivative is greater than 0. And so this is concave up here. And then the opposite was concave down. The second derivative here is negative, which means the slope is getting, how is the slope changing? The slope is getting less positive, more negative. Second derivative is negative, so it's concave down. And these points P are where it switches over. And those are the inflection points. And you can imagine if over here the second derivative is greater than 0 because it's getting more positive, and here the second derivative is less than 0. It's got to be 0 somewhere in between, right? If here it's positive, here it's negative, and at the inflection points like this, these simple inflection points, the derivative is 0. So at an inflection point in between where it's concave up to concave down, the inflection point will have the second derivative equal to 0. That's not always the case though, so you got to be careful of that. But typically in a nice smooth curve, that's what you're going to find. If it switches over from positive to negative in between, it's got to be 0 somewhere, and those are the inflection points. So one way to find inflection points on a simple curve is where the second derivative is 0. Okay, so now we have this second derivative test, another red box. So let's say we have a nice second derivative. It's not some weird thing. So if the first derivative is 0, that means it's flat, right? So it's probably a peak, a minimum, or a maximum. And the second derivative at that point is greater than 0, then it's a local min. Okay, so like right here. Here the slope is 0. Can you see that there? There the slope is 0 in this curve. And if you take the second derivative, the way the slope is changing is getting more positive, so second derivative is greater than 0, so it's a local minimum, it's at the bottom. So of course the opposite, if its slope is 0 and the second derivative is less than 0 there, then it's a local maximum. So that's one thing we're going to be using in a lot of the problems. You find where the slope is 0, what points the slope is 0, take the second derivative, see if it's negative or positive there, and right away you know if it's a min or a maximum. So there's two ways, this is the important part, there's two ways to figure out if it's a minimum or maximum without, graphing it on decimals, which is a great way to check your answers, so use decimals. But there are two ways. You can take the first derivative, find where it's 0, then do the second derivative, and see if it's greater or less than 0. Or you can just use the first derivative, and you can see if it goes from negative to positive. So here the slope switches from negative, and here it goes to positive. The problem with that technique is you got to choose a number, like, okay, let's say this number is 2. The bottom is 2. Then you plug into your first derivative 1.5 or 1.9, number really close to 2, and see what the slope is. And then you plug a number like 2.1 into your f prime formula and see what the slope is. And then if it's positive on one side, or negative on one side, positive on the other side, you know it's a minimum. If it's positive and positive, you know it's an inflection point. Like here it's positive, positive, and positive, you know it's an inflection point. If it's negative and negative, you know it's an inflection point. But if the slope is, let's see, negative, positive, you know it's a minimum, or positive to negative, you know it's a maximum. It's kind of a pain, right? You got to plug in numbers. You just got to choose a number that's maybe easy. One, if this is 2, plug in 1.9, plug in 2.1 into your derivative formula. Yeah, it's kind of a hassle, but that's one way to tell if it's a min or max. And then the second way is the second derivative test. Just take the second derivative and plug in the number. I think that's cleaner and easier. But you do have two ways that you can do it. Okay, so then they go through some examples in the book, lots of examples in the book, and that's pretty much the end of that section. Let's look at some of these problems here that are just picture problems. Like this graph here, what can we say about where it's concave up and concave down? Okay, so I know it's kind of small in the video, but let's look at this graph here. Okay, somewhere in here, we don't know unless we have a formula and figure it out, but somewhere right in here, maybe right there, is an inflection point. It's going from concave up to concave down. Okay, so somewhere right there, and we have to guess because we can't take this second derivative and see where it's 0. We have an inflection point. Here it's concave up, here it's concave down. From here to here it's increasing, and then decreasing, and then increasing, and then decreasing, and then decreasing. Okay, so this point here, it goes from concave down to concave down. So that's not an inflection point. Inflection points are where the slope switches over from getting less and less negative to more and more positive or whatever. That doesn't happen here. If it goes concave down, it's just an interesting point. And it is a critical number because the slope is undefined. Sharp points, the slope are undefined. That's a critical number. Doesn't have a slope equals 0, right? It's a sharp point. Okay, this here is also a critical number. The slope does not exist. And it goes from concave down, and this curve is going this way, so it goes to concave up. So you would say that x equals 7 is an inflection point, because at that point it switches over from concave down to concave up. So that critical number there is an inflection point. The slope is undefined, right? But it goes from concave down to concave up. And of course we have a local maximum, a local maximum, a local minimum. Here's another local minimum. Okay, those are kind of things we can say about this thing, like where is it increasing? And increasing and decreasing is like the easiest thing. Just where is it going uphill? Where is it going downhill? Where is it going uphill? And you just say, okay, from x equals 0 to 3, and then you just read the points off the graph. Or if you graphed it yourself, you can get the exact numbers. Okay, those are the overall ideas in section 4.3. I would use the book or write them down. Everything in a red box is really important to keep those ideas in mind as we do some problems. So hope that helps.